Imagine a spinning top sitting alone in the middle of an empty room. Now imagine that simply by spinning, it could reach out and slowly turn a second top floating nearby. No string, no magnet, no puff of air, no contact of any kind, just rotation, quietly twisting the space around it. This sounds impossible. Nothing is touching. And yet something remarkably like this happens around every rotating mass in the universe, from our own planet to collapsed stars so dense they bend passing light. A rotating object does not merely move through space, it takes hold of space and time and carries them partway around with it. Clocks feel it, spinning gyroscopes feel it, even beams of light feel it. The strangest part is that nothing is being pushed at all. So how can rotation pull on matter it never touches? If exploring questions like this is the kind of thing you enjoy, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. Picture two skaters gliding across a frozen lake. One of them begins to spin in place, arms tucked in, turning faster and faster. The other skater is standing several feet away, not holding any rope, not touching the first skater at all, just resting quietly on the ice. And yet, somehow, the second skater begins to slowly turn. Not because of wind, not because the ice is tilted, not because anyone reached out and gave a push. The mere act of the first skater spinning has reached across the empty gap and started to rotate the other one. On a frozen lake, this is pure fantasy. There is nothing in everyday life that behaves this way. But replace those skaters with something far more massive, something like a planet, or a collapsed star, or a black hole. And this fantasy becomes a genuine prediction of how the universe actually works. A spinning mass really can take hold of the matter around it and carry it partway around, with nothing physically connecting the two. To understand how that is even possible, we have to throw out almost everything our intuition tells us about what gravity is and rebuild the picture from the ground up. Let us start with the version of gravity most of us carry around in our heads. From the time we are small children, we learn that things fall. You drop an apple and it drops to the floor. You toss a ball into the air and it arcs back down. The earth, we are told, pulls on everything around it. There is an invisible force reaching out from the planet, grabbing hold of objects and dragging them downward. This is the picture that Isaac Newton gave the world more than 300 years ago, and for everyday purposes, it works beautifully. It predicts the path of a cannonball, the orbit of the moon, the timing of the tides. Newton imagined gravity as a force acting at a distance, an invisible tether stretching between any two objects in the universe, pulling them toward one another. The more massive the objects, the stronger the pull. The farther apart they are, the weaker it becomes. It is clean, simple, and for a very long time it seemed to be the final word. But there was always something deeply strange hiding inside Newton's idea, something that bothered even Newton himself. How does the pull actually get from one object to the other? When the Earth tugs on the moon, what is doing the tugging? There is no rope, no rod, no chain stretching across the 250,000 miles of empty space between them. The force just somehow acts across the void, instantly, with nothing in between to carry it. Newton wrote down equations that described how strong the pull would be, and those equations matched the heavens with stunning accuracy. but he openly admitted he had no idea what gravity really was. He had described its behavior without explaining its nature. For 2 centuries, that gap sat there, papered over by the usefulness of the math. Then, a little over 100 years ago, Albert Einstein came along and reimagined the whole thing. His insight was so radical that it still takes effort to absorb today. Einstein proposed that gravity is not a force pulling objects through space at all. Instead, gravity is a feature of the shape of space and time themselves. Mass and energy, he said, bend and warp the geometry of the universe around them, and what we experience as gravity is simply matter moving through that warped geometry. There is no invisible tether. There is no reaching hand. There is only the shape of the stage on which everything moves, and that shape is sculpted by the things sitting on it. Now, almost everyone has heard the famous image used to explain this. You take a stretchy rubber sheet, pull it tight, and place a heavy bowling ball in the middle. The sheet sags downward, forming a dip. Then you roll a small marble nearby, and instead of travelling in a straight line, it curves toward the bowling ball, spiralling around the dip. The bowling ball is like the sun, the marble is like a planet, and the sagging sheet is supposed to represent the warping of space. This image is genuinely useful as a first step, and I will not take it away entirely. It captures something true, that mass changes the geometry around it, and that objects respond to that changed geometry rather than to a direct pull. But I have to be honest with you, because this image is also deeply misleading, and if you hold on to it too tightly, you will end up more confused than before. Here is the first problem. The rubber sheet only sags because there is already gravity pulling the bowling ball downward. We are using gravity to explain gravity, which is circular and tells us nothing fundamental. The second problem is even bigger. A rubber sheet is a 2-dimensional surface, bending into a 3rd dimension, into a direction we can see and point to, called down. But real space-time is not bending into some extra visible direction that lies off to the side of our universe. There is no edge of space we could fly to and look back and watch the dimple from the outside. The curvature Einstein described is something the geometry has all on its own, woven into the very fabric of distances and durations, with no need for an outside direction to bend into. And the third, most important problem is this. The rubber sheet leaves out time entirely. And time, it turns out, is where most of the action actually happens. For an object moving slowly compared to light, like you, or a falling apple, or the moon, the bending of time matters far more than the bending of space. So please, keep the rubber sheet in your back pocket as a rough sketch, but understand that the real picture is about geometry, the genuine relationships between points in space and moments in time, and not about a literal fabric draped over a frame. So, if gravity is not a force, then why do things fall? This is the question that unlocks everything that follows, so let us take it slowly. Einstein's answer is that a falling object is not being pulled by anything at all. A falling object is simply following the straightest possible path available to it through curved space-time. We have a name for the straightest possible path through a curved geometry. We call it a geodesic. On the flat surface of a tabletop, the straightest path between 2 points is an ordinary straight line, the kind you could draw with a ruler. But on the curved surface of the Earth, the straightest possible path is different. If you start walking and never turn left or right, never deviate, just keep going as straight as you possibly can, you will eventually trace out a great circle around the entire planet. Airline pilots flying from one continent to another follow exactly these paths, which is why a flight route drawn on a flat map often looks like a strange curve arcing far to the north. The plane is not taking a detour. It is following the straightest line available on a curved surface. The curvature of the surface is what makes the straight path look bent to us. Now extend that idea from a curved surface to curved space-time, and you have the heart of Einstein's gravity. The Earth is not reaching up and pulling a falling apple downward. The Earth has curved the space-time around it, and the apple, released from your hand, simply follows the straightest available path through that curved geometry. From our point of view standing on the ground, that straightest path happens to lead the apple toward the center of the planet, so the apple falls. The apple is doing the most natural, the most effortless thing it can possibly do. It is moving in a straight line through a region where straight lines bend toward the Earth. There is no force acting on it. In fact, and this is one of the most beautiful and counterintuitive ideas in all of physics, a falling object feels no force whatsoever. An astronaut floating in orbit is weightless, not because gravity has switched off, but because they are in perfect freefall, following their natural geodesic with nothing pushing or pulling against them. The only time you actually feel gravity, the only time you feel that pressure on the soles of your feet, is when the ground pushes up against you and stops you from following your natural falling path. The push you feel is the floor, not the planet. Let me make this even stranger, because it is worth sitting with. If gravity is the curvature of space-time, and if the curvature of time matters more than the curvature of space for slow-moving objects, then in a very real sense, you are falling toward the Earth right now, because time itself ticks at slightly different rates at your head and at your feet. Clocks closer to a massive object run slightly slower than clocks farther away. This is not a trick or an illusion. It has been measured directly, with clocks placed at different heights, and even with clocks separated by just a single foot of elevation. Your feet are, right now, aging very slightly more slowly than your head. And objects, when left to move freely, naturally drift toward regions where time runs slower. The apple falls because the future, in a sense, lies in the direction of the slower clocks down below. This is profoundly different from a rope pulling it down. It is geometry, the geometry of time and space, quietly steering matter along its straightest course. Now, before we can get to the truly mind-bending part, the part about rotation, we have to nail down one more idea, because the whole mystery of the title hinges on it. We have to talk about what a reference frame actually is. The phrase sounds technical, even intimidating, but the idea is simple, and you use it every single day without realizing it. A reference frame is just a point of view from which you measure where things are and how they move. It includes a sense of which way is up, which way is down, which directions count as left and right, and crucially, what it means to be standing still versus turning around. Think about sitting on a train. If the ride is smooth and the windows are covered, you cannot tell whether the train is sitting in the station or gliding along the tracks at a steady speed. From inside your sealed train car, everything behaves normally. A cup of coffee sits still on the table. A dropped pen falls straight down. There is no experiment you can do inside that sealed car to determine whether you are moving or not, as long as the motion is smooth and unchanging. This is one of the oldest and deepest principles in physics, going all the way back to Galileo. Steady motion in a straight line is, in a sense, indistinguishable from rest. Your sealed train car is what physicists would call an inertial frame, a point of view in which objects left alone simply stay still or keep moving steadily, with nothing strange happening to them. But now imagine the train suddenly speeds up or slams on the brakes, or rounds a sharp curve. Instantly, everything changes. Your coffee sloshes, your body gets pressed back into the seat or thrown to the side. The pen, when dropped, no longer falls straight down, but veers off at an angle. Now you absolutely can tell that something is happening without looking out the window at all, because objects inside your car are being pushed around in ways that betray the change. A frame that is accelerating or turning is not an inertial frame. It is a frame in which mysterious-seeming pushes appear, the very pushes that throw you sideways on a sharp turn. So here is the deep question that Einstein's whole framework forces us to confront. When you are spinning, how do you know you are spinning? On a merry-go-round, you can feel yourself being flung outward. Close your eyes and you can still tell you are turning because of that outward pull and the dizziness it produces. But spinning relative to what? What is the thing you are turning with respect to? For most of history, the answer seemed obvious. You are spinning relative to space itself, relative to some fixed, absolute backdrop against which all motion is measured. And there was a second answer that seemed to agree with the first. You are spinning relative to the distant stars. Stop spinning and the stars hold still. Start spinning and the whole sky appears to wheel around you. The fixed stars far away seem to define what it means to not be rotating. A gyroscope, a spinning wheel mounted so it can swivel freely, will hold its orientation rock steady, pointing at the same distant star night after night, no matter how you turn the frame around it. The non-spinning gyroscope and the distant stars seem to be locked in perfect agreement about which directions count as fixed. Hold on to that idea, because it is exactly the thing that rotation is going to disturb. The distant stars and a freely spinning gyroscope define a local sense of what it means to not be rotating. They tell you which way is the unchanging, non-turning reference. And the astonishing claim we are building toward is that a massive object, simply by rotating, can shift that local sense of non-rotation. It can change which directions count as standing still. It can take the very definition of not turning, the definition handed to us by the distant stars, and quietly drag it around. But to see how, we first have to be completely clear that ordinary gravity, the kind we have been describing so far, does not do this at all. Consider a perfectly round, non-rotating planet, just sitting there in space, not spinning, perfectly still. It has mass, so it curves the space-time around it. Drop an object near it, and the object falls inward along its geodesic, following the straightest path through the curved geometry, heading toward the center. Send an object past it at an angle, and the object's path bends, curving around the planet, perhaps settling into an orbit. Light passing nearby gets deflected, its path bending around the mass. Clocks near the surface run slow compared to clocks far away. All of this happens with a perfectly still, non-rotating planet. None of it requires any spin whatsoever. The curvature produced by a stationary mass is purely about pulling inward, about drawing geodesics toward the center, about slowing time deep in the gravitational well. There is no twist to it, no swirl, no sideways carrying of frames. It is, if you like, a perfectly symmetric dimple in geometry, the same in every direction around the planet. Spin the planet down to a complete stop, and the geometry has no sense of rotation built into it at all. This is the crucial baseline, so let me emphasize it. Ordinary gravity, the gravity of a mass that just sits there, pulls things inward. It bends paths toward the center. It can hold a moon in orbit, crush a star, trap light. But it has no preferred direction of swirl. A gyroscope falling freely toward a non-rotating, perfectly symmetric mass will keep pointing at the same distant star the entire way down. Its orientation will not drift, will not precess, will not slowly rotate. The distant stars and the gyroscope stay in agreement, because there is nothing about a stationary mass that could possibly disturb that agreement. The geometry has no handedness, no clockwise or counterclockwise preference. It is the same whether you imagine the planet's left side or its right. So everything we have built so far, the whole magnificent edifice of Einstein's gravity, gives us a universe where mass curbs space-time, where falling objects follow the straightest available paths through that curvature, where there is no pulling force, but only geometry steering matter, and where a stationary mass produces a clean, symmetric, inward-tugging warp with no swirl to it whatsoever. That is the complete picture for an object that does not rotate. And for an enormous range of situations, that picture is more than enough. It explains why apples fall and planets orbit, and light bends and clocks slow. But the universe is full of things that spin. Planets spin. Stars spin. When stars collapse at the ends of their lives, they spin faster, sometimes hundreds of times every second. Black holes spin, sometimes at very nearly the maximum rate the laws of physics allow. And here is the question that should be glowing in your mind by now. If a stationary mass curves space-time into a clean inward dimple, what does a spinning mass do? Does rotation simply add a little extra curvature, a slightly deeper dimple? Or does it do something genuinely new, something the stationary case never hinted at? The answer is that rotation does something genuinely new, and this is the entire heart of our story. A rotating mass does not just curve space-time inward, it twists it. It takes the geometry around it and gives it a swirl, a directional sense of rotation that the stationary case completely lacks. And because that swirl is built into the geometry, into the very definition of which directions count as non-rotating, anything moving freely through that region gets caught up in it. The geometry that defines standing still is itself dragged around in the direction of the spin. A gyroscope that should hold steady, pointing at a fixed, distant star forever, will instead very slowly turn. Not because anything touched it, not because any torque was applied to its axle, but because the local definition of not turning has itself been carried around by the rotation of the mass. This is the effect that lives at the center of everything we are exploring, and it has a name. Physicists call it frame dragging, because the rotating mass quite literally drags the reference frames around it. The spinning object reaches out, not with a force, not with a rope, not with any contact at all, but through the geometry of space-time itself, and it carries the local sense of rest partway around with it. The matter nearby is not pushed. The light nearby is not pushed. The gyroscopes nearby are not pushed. And yet all of them slowly acquire a turning motion, a swirl, inherited from the geometry that the rotation has reshaped. They are following their straightest possible paths, just as a falling apple does, just as an orbiting moon does. It is only that the straightest possible paths now have a twist baked into them, because the geometry itself has been set spinning, in a sense we will have to make very precise. I have to pause here and place a careful warning, because the words I just used are dangerous if taken too literally. When I say the geometry has been set spinning, I do not mean that space-time is some kind of liquid or whirlpool sloshing around the rotating mass like water circling a drain. There is no substance there to slosh. Space-time is not a material that physically grabs hold of matter and spins it around through friction or contact. That image, like the rubber sheet, is a stepping stone, and we will have to replace it with something more accurate before we are done. What is really happening is that the rotation of the mass changes the relationships between points in space and moments in time, changes which directions a freely moving object will naturally drift toward, changes the very meaning of holding still. The swirl is in the geometry, in the rules that govern motion, not in some swirling fluid. And the matter that responds to that swirl is not being touched. It is interacting with the rotating mass gravitationally through the shape of space-time in exactly the same way a falling apple interacts with the Earth, through geometry alone, with no contact and no pulling hand. That is the promise of the title, and now you can begin to see how it could possibly be true. Rotating space-time can drag matter without touching it, because in Einstein's universe, gravity never works by touching anything in the first place. Gravity is geometry, and geometry steers matter, whether the mass is still or spinning. A stationary mass steers matter inward. A rotating mass steers matter inward and also gives it a twist. In both cases, nothing reaches out and grabs. In both cases, the matter is simply following the straightest path it can find through a landscape that the mass has reshaped. The only difference is that a spinning mass adds a swirl to that landscape, a swirl tied directly to how much it spins and how much mass it carries, a swirl that fades with distance but never quite vanishes. And so the spinning skater on the frozen lake, the one who somehow turns the other skater across an empty gap, is not such a fantasy after all. It is a faint, almost imperceptible version of something the universe does around every rotating mass, including the very planet beneath your feet. The Earth, turning once each day, is dragging the space-time around it ever so slightly, twisting the local frames, nudging gyroscopes off their fixed stars by an amount so tiny it took some of the most precise instruments ever built to detect it. The effect is real, it is measurable, and it grows from a whisper near Earth into a roar around the most extreme objects in the cosmos. But the mechanism is always the same. A spinning mass reshapes the geometry of space and time, and matter, light, clocks, and gyroscopes follow that reshaped geometry, carried partway around by a rotation they never physically touch. How a planet does this with the gentlest of nudges, and how a spinning wheel can reveal the twist hidden in empty space, is exactly where we turn next. There is a quantity in physics that measures not just how much something is spinning, but how stubbornly it keeps spinning, how much rotational oomph it carries. We call it angular momentum, and it is the key that unlocks the difference between a still mass and a turning one. You already have an instinct for it, even if you have never heard the term. A spinning top, once set going, wants to keep going. A bicycle wheel, spun up fast, resists being tilted and seems to fight back against your hands. A figure skater pulling her arms inward spins faster, and throwing them outward slows down. All of these are angular momentum at work, the tendency of a turning thing to stay turning. What matters most for our story is what angular momentum depends on, because this is what determines how strongly a rotating mass can twist the space-time around it. Angular momentum depends on three things working together. First, it depends on how much mass there is. A heavier object carries more rotational momentum than a lighter one, turning at the same rate. Second, it depends on how fast the object rotates. Something spinning 1,000 times a second carries far more than the same object turning once a day. And third, it depends on how the mass is spread out, on how widely it is distributed from the axis of rotation. Mass far from the center of the spin contributes much more than mass packed close to the axis. This is why a figure skater speeds up when she pulls her arms in. By drawing her mass closer to the axis, she changes the distribution, and since her total angular momentum is conserved, her rotation rate has to climb to compensate. So when we ask how powerfully a spinning body will reach out and drag the geometry around it, the answer comes down to this single combined quantity. More mass, faster spin, and wider distribution all feed into a larger angular momentum. And a larger angular momentum means a stronger twist imprinted on space-time. Now we can be precise about what that twist actually does, and we can finally pin down the phrase that gives this whole subject its name. We have been saying that a rotating mass drags the local frames around it. But what does it really mean to drag a frame? Let us go back to the idea we built carefully in the beginning, the idea of a reference frame as a point of view that includes a sense of what it means to not be rotating. Remember that a freely spinning gyroscope, far from any massive object, will hold its orientation steady, pointing at the same distant star indefinitely. And remember that the distant stars themselves seem to define the unchanging, non-rotating directions of space. Out in the emptiness, far from any mass, the gyroscope and the distant stars agree completely. The gyroscope points at a star, and it stays pointed at that star because there is nothing around to disturb it. That agreement is what it means to have a well-defined sense of non-rotation. The local definition of not turning, set by the gyroscope, lines up perfectly with the distance definition of not turning, set by the stars far away. Frame dragging is the breaking of that agreement. Bring a massive rotating body into the picture, and something subtle but profound happens. The local sense of non-rotation, the sense defined by gyroscopes and by freely falling matter right there near the spinning mass, no longer lines up with the distant stars. The rotation of the mass carries the local definition of not turning around with it, in the direction of the spin. A gyroscope sitting near the spinning body, a gyroscope that should hold its orientation fixed on a distant star, will instead very slowly turn, its axis sweeping around in the same direction the mass is rotating. To an observer watching from far away, beside the distant stars, the gyroscope appears to precess, to wobble its pointing direction in a slow, steady drift. But here is the heart of it. From the gyroscope's own local point of view, it is not turning at all. It is doing exactly what a free gyroscope always does, holding steady against its local surroundings, refusing to rotate relative to the geometry right around it. It is just that the geometry right around it has itself been set turning by the spinning mass. The local frame, the local definition of standing still, has been dragged around, and the gyroscope, faithfully holding still relative to that dragged frame, ends up slowly rotating relative to the distant stars. This is why dragging a frame is not just poetic language. It is a literal change in which directions count as non-rotating. Near a spinning mass, the answer to the question, "What does it mean to not be turning?" is different from the answer the distant stars would give. The two definitions have come apart, and the gap between them is the frame dragging. The faster and more massive the spin, the wider that gap. The whole local arena of standing still has been picked up and carried partway around in the direction of rotation, and everything that tries to hold still locally gets carried along with it. I want to dwell on why a gyroscope is the perfect tool for revealing this, because it is genuinely beautiful how well suited it is. A gyroscope is, at its core, a spinning wheel mounted so that it can pivot freely in any direction, with as little friction in its bearings as humanly possible. The defining property of such a device is that it resists changes to its orientation. Once spinning, its axis wants to keep pointing in the same direction, no matter how you turn the housing around it. This is why gyroscopes are used to keep ships steady, to guide aircraft, to stabilize cameras and spacecraft. You can rotate the entire frame around a good gyroscope, and its axis will stubbornly hold its line. And the deepest reason it holds its line is that, left truly free, it has no way to change its orientation unless something exerts a twisting force on it, what physicists call a torque. No torque, no change in pointing direction. That is the unbreakable rule for an ideal gyroscope. So now you can see the trap closing on the mystery. If a gyroscope only changes its orientation when a torque acts on it, and if we build a gyroscope so exquisitely free that no ordinary torque can reach it, then it should point at the same distant star forever. And yet, near a rotating mass, It does not. It slowly drifts. It precesses. So either some hidden torque is sneaking in, or our rule about torques is incomplete. The astonishing resolution is the second one. There is no torque acting on the gyroscope at all. Nothing is twisting its axle. Nothing is pushing on its frame. The gyroscope is in perfect free fall, following its natural path through space-time, experiencing no force and no twist of any conventional kind. And it still precesses, because the geometry it is embedded in has been dragged around by the rotating mass. The gyroscope is the ideal detector precisely because it has no business changing its orientation. When it does change, when it drifts off its fixed star with no torque anywhere in sight, it is telling us something about the geometry itself. It is reading out the swirl in space-time the way a compass needle reads out a magnetic field, except here there is no field of the ordinary kind, only the twisted shape of space and time. This is the moment to be absolutely clear about what frame dragging is not, because the danger of confusion is enormous. The slow precession of our gyroscope looks, on the surface, like the kind of wobble you might get from a perfectly mundane cause, and we have to rule every one of those out to see what is special here. The first thing it is not is a mechanical torque from contact. If you reach out and flick a spinning top, you apply a contact force, a touch, and the top responds. But our freely floating gyroscope is touched by nothing. There is no hand, no surface, no rod, no friction in its bearings nudging it along. Whatever is turning it, it is not contact. The second thing it is not is a magnetic effect. A magnetized gyroscope sitting in a magnetic field will feel a genuine twisting force, and it will precess in response. This is a real and well-understood phenomenon, and engineers go to great lengths to shield sensitive gyroscopes from stray magnetic fields for exactly this reason. But frame dragging needs no magnetism and no electric charge whatsoever. A perfectly uncharged, unmagnetized gyroscope, made of material that responds to no magnetic field at all, still precesses near a rotating mass. The effect does not care whether the gyroscope is magnetic or not, because it is not magnetic in nature. It is gravitational, written into the geometry, reaching every object regardless of its electrical properties. The third thing it is not, and this one is the subtlest, is an ordinary lopsided gravitational tug. Even in plain Newtonian gravity, without any of Einstein's curvature, a non-spherical mass can exert a twisting effect on an extended object nearby. The Earth, for instance, is not a perfect sphere. It bulges slightly at the equator. That bulge means the gravitational pull on a nearby orbiting body is not perfectly even, and that unevenness can cause an orbit to slowly precess, to slowly rotate its orientation over time. This is a real effect, and it is large, and it has nothing to do with frame dragging. It comes purely from the shape of the mass, from the fact that one part of it is closer or more massive in a given direction than another. Crucially, this Newtonian precession does not depend on whether the mass is spinning. Freeze the Earth's rotation completely, keep the equatorial bulge, and you still get this orbital precession from the uneven distribution of mass. Frame dragging is something entirely different. It depends on the rotation itself, on the angular momentum, on the actual turning of the mass. Stop the spin and frame dragging vanishes, even though the lopsided Newtonian tug would remain. This is how physicists can tell the two apart. They must carefully calculate and subtract every ordinary effect, every consequence of the mass's shape and uneven pull, and only what remains, the part that exists solely because the mass is rotating, is the true frame-dragging signal. It is a small residue left behind after all the familiar effects are accounted for, and isolating it is one of the great challenges of measuring this phenomenon at all. So we have a precession that comes from no contact, no magnetism, and no mere lopsidedness of pull, a precession that exists only because the central mass is turning. That is the fingerprint of frame dragging, and it is unmistakable once you know to look for it. Now let us ask the obvious next question. How big is this effect? If the Earth beneath us is spinning, and spinning masses drag space-time, then surely the ground we stand on is twisting the geometry around us right now. Why have we never noticed? Why does a spinning top on a table not slowly turn its neighbour across the room? Why did it take until the 21st century to even detect this around our own planet? The answer lies in the two factors that govern the strength of frame dragging, and both of them work against us here on Earth. The first factor is angular momentum, the quantity we discussed at the start. The stronger the angular momentum of the central mass, the stronger the drag. And while the Earth is enormous by human standards, with a tremendous mass, it rotates only once every 24 hours. That is, in cosmic terms, extraordinarily slow. A point on the equator is moving at something like 1,000 miles per hour, which sounds fast, but compared to the speeds at which truly extreme objects rotate, it is a crawl. The Earth's angular momentum, large as it is, produces only the faintest twist in the surrounding geometry. The second factor is distance. Frame dragging, like gravity itself, weakens as you move away from the source, and it weakens quite rapidly. Close to a spinning mass, the drag is strongest. Far away, it fades toward nothing. And we, standing on the surface or orbiting in spacecraft a few hundred miles up, are actually quite far from the Earth's center in the terms that matter, far enough that the already weak twist has faded further still. Put those two factors together, a slowly rotating planet of modest angular momentum observed from a respectable distance, and you get a frame dragging effect that is almost unimaginably tiny. To give you a sense of the scale, the rate at which a gyroscope in orbit around the Earth would precess due to frame dragging is measured in milli-arcseconds per year. An arcsecond is already a minuscule angle, just 1/3600th of a single degree, about the width of a small coin seen from several miles away. A milli-arcsecond is 1,000 times smaller than that. And the Earth's frame dragging drifts a gyroscope by only a few dozen milli-arcseconds over an entire year. This is a deflection so small that detecting it pushes against the very limits of what human technology can achieve. It is like trying to measure the slow turn of a clock's hand by watching it move a distance thinner than an atom across the face of the dial. For most of the 20th century, this effect was purely theoretical. The mathematics predicted it, flowing inevitably out of Einstein's equations the moment you allowed the central mass to rotate. Two physicists worked out the detailed prediction in the years just after Einstein published his theory, calculating exactly how a gyroscope should precess near a spinning body. But predicting it and measuring it are worlds apart. To actually catch the Earth dragging space-time, you would need gyroscopes of a perfection never before achieved. Gyroscopes so flawless and so free of every ordinary disturbance that a drift of a few milli-arcseconds per year could be cleanly separated from all the noise. This is exactly the challenge that one remarkable experiment set out to meet, and I want to describe it, though I will keep the focus on the physics rather than on the engineering saga, because the lesson is in what was measured, not in the decades of struggle to build the instrument. The idea was elegant in its simplicity. Place a set of gyroscopes aboard a satellite in orbit around the Earth, point them at a chosen distant star, and let them fall freely around the planet, watching to see whether their axes drifted away from that star. If Einstein was right, the gyroscopes should slowly precess, dragged around by the Earth's rotation, by an amount the theory predicted in advance. If Einstein was wrong, they should hold perfectly still on their star. The gyroscopes built for this purpose were among the most perfect objects ever manufactured by human hands. They were spheres, and they were so close to perfectly round that if you scaled one up to the size of the Earth, the tallest mountain, and the deepest valley on its surface would differ by only a few feet. This near-perfect roundness mattered enormously, because any lump or asymmetry in the spinning sphere could introduce its own spurious wobble, a fake signal that would drown out the real one. The spheres were spun up, suspended without touching anything, floating freely so that no bearing, no contact, no friction could exert the slightest torque on them. They were shielded from magnetic fields with extraordinary care, because, as we discussed, a stray magnetic field acting on any trace of magnetism in the sphere could mimic the precession they were hunting for. Everything that could possibly twist a gyroscope by ordinary means was hunted down and suppressed, so that whatever drift remained could be attributed to space-time itself. And there was a complication that beautifully illustrates the point we made earlier about telling frame dragging apart from everything else. The Earth's frame dragging is not the only thing that makes an orbiting gyroscope precess. There is a much larger effect, also predicted by Einstein, that comes simply from the gyroscope moving through the curved space-time around a massive body, even if that body were not rotating at all. This larger effect is the precession caused by the curvature of space itself, by the geometry that even a stationary Earth would produce. It is bigger than the frame dragging by a wide margin, on the order of 100 times larger. So the experimenters faced a delicate task. They had to measure two precessions at once, a large one from the mere curvature around the Earth, and a much smaller one from the Earth's rotation dragging the frames. The two effects even point in different directions, one drifting the gyroscope's axis one way, the other drifting it along a perpendicular line, which is what made it possible to separate them. By measuring the drift in two perpendicular directions, the large curvature effect and the small dragging effect could be teased apart, each compared against what Einstein's equations had foretold. It is worth lingering on why those two precessions point in perpendicular directions, because the geometry is elegant, and it is what made the whole measurement possible. Picture the satellite circling the Earth in its orbit, with the gyroscope inside pointing at its chosen distant star. The larger of the two effects, the precession caused by the mere curvature of space around the Earth, arises from the gyroscope being carried around the planet through curved geometry. As the gyroscope sweeps along its orbital path, the curvature of space causes its axis to slowly tip within the plane of the orbit, drifting in the same plane that the satellite traces out as it circles the Earth. Think of it as a drift that lives in the flat sheet of the orbit itself, accumulating a little more with every loop the satellite completes around the planet. The frame-dragging precession, by contrast, does not live in that plane at all. It comes not from the gyroscope being carried through curved space, but from the Earth's rotation twisting the local frames around the spin axis of the planet. And that twisting drags the gyroscope's axis in a direction perpendicular to the orbital drift, sideways relative to the larger curvature effect. One precession tips the gyroscope within the plane of its orbit, the other nudges it out of that plane, off to the side, in the direction the Earth's rotation is carrying the local frames. Because the two drifts are at right angles to one another, they do not blur together into a single muddled motion. They can be measured independently, each along its own axis, like measuring how far a target has moved both left to right and up and down as two separate numbers. This perpendicular arrangement is a tremendous gift to the experimenter. If the two effects had pointed in the same direction, the tiny frame dragging signal would have been hopelessly buried inside the much larger curvature signal, a small whisper lost beneath a shout in the same ear. But because nature places them at right angles, the large curvature precession could be measured along one direction and effectively set aside, while the small frame-dragging precession could be hunted along the perpendicular direction, where the larger effect contributes nothing. The experimenters were, in effect, listening for two different notes coming from two different directions at once, and the geometry of general relativity itself arranged for those notes to arrive cleanly separated. Without that perpendicular separation, catching the Earth's frame dragging with gyroscopes might have been impossible. With it, the faint rotational drift could be teased out, isolated, and compared directly against the theory's prediction. When the results finally came in, after years of painstaking analysis to scrub away every last source of error, both effects were there. The large precession from spatial curvature matched the prediction, and the small precession from frame dragging, the drift caused purely by the Earth's rotation carrying the local frames around, was also detected, in agreement with what the theory had predicted, within the uncertainties of the measurement. The Earth, spinning silently beneath the satellite, really was dragging the space-time around it, really was twisting the local definition of non-rotation, really was nudging those perfect gyroscopes off their distant star by a few milli-arcseconds a year, exactly as a 100-year-old calculation had promised. I want to be honest about the precision here, because it matters. This was a difficult measurement, and the frame dragging part of it carried a larger uncertainty than the experimenters had originally hoped, owing to subtle disturbances on the gyroscopes that took enormous effort to model and remove. It was not a measurement of limitless precision, but it was a genuine detection, a confirmation that the effect is real, and of roughly the size Einstein's theory demands. And it stands alongside other independent efforts that have looked for the same dragging through different means, such as tracking the slow shift of satellite orbits caused by the same twist in the geometry. And this is the lesson I most want you to carry forward. The frame dragging around the Earth is real. It is not a mathematical fiction or a theorist's daydream. It has been measured, with instruments of staggering delicacy, and the spinning planet beneath your feet is, at this very moment, twisting the fabric of space-time around it, carrying the local frames a tiny fraction of the way around with each rotation. But it is also, around the Earth, almost vanishingly small, a whisper at the very threshold of detection, requiring near-perfect spheres and decades of effort to catch it all. The twist is there, but it is gentle beyond imagining, because the Earth, for all its bulk, spins slowly, and we observe it from afar. That gentleness, though, is a feature of our particular circumstances, not of the phenomenon itself. The two factors that made the effect so tiny here, modest angular momentum and considerable distance, can both be pushed in the opposite direction. Imagine a mass far greater than the Earth, compressed into a far smaller space, spinning not once a day, but hundreds of times every second. Imagine getting not hundreds of miles from its center, but skimming right along its surface, where the dragging is fiercest. Crank up the angular momentum to extremes the Earth could never approach, and shrink the distance to the bare minimum, and the whisper becomes a roar. The same effect that barely deflects a perfect gyroscope in orbit around our planet can, around the right object, seize matter so powerfully that standing still becomes flatly impossible, that the very notion of holding your position against the spin breaks down entirely. There are objects in the universe where rotation does not merely nudge the local frames, but commands them, where the dragging of space-time is not a delicate correction, but a dominant force shaping everything nearby. To find them, we have to seek out the most extreme spinning masses the cosmos has to offer, the collapsed remnants of dead stars and the dark, turning hearts of black holes. And that is exactly where our journey takes us next. Out in the universe, when a massive star reaches the end of its life and can no longer hold itself up against its own gravity, it collapses. The outer layers may blast away in a tremendous explosion, but the core falls inward, crushing matter to densities that defy imagination. And as it collapses, something dramatic happens to its rotation. Recall the figure skater pulling her arms inward, spinning faster and faster as her mass draws closer to the axis. A collapsing stellar core does the same thing, but to an extreme no skater could ever approach. A star that may have taken weeks to turn once, when crushed into a sphere only a few miles across, can end up spinning hundreds of times every second. The angular momentum that was spread across an enormous star is now concentrated into a tiny, ferociously dense ball. And as we learned, angular momentum is exactly the ingredient that determines how strongly a mass twists the space-time around it. Here, then, is where frame dragging stops being a whisper and starts becoming a defining feature of the geometry. Consider a neutron star, the collapsed core left behind by certain dying stars. It packs more mass than our entire Sun into a sphere you could drive across in a few minutes. A single sugar cube-sized piece of it would weigh as much as a mountain. And many of these objects spin with blistering speed, the fastest completing several hundred full rotations in a single second. Take that immense mass, that breathtaking density, and that furious spin, and combine them, and you get an angular momentum vastly beyond anything the Earth could muster. The frame dragging around such an object is correspondingly stronger, no longer a few milliarc seconds a year, but a genuine, sizable twisting of the geometry that nearby matter cannot ignore. The local frames near a fast-spinning neutron star are dragged around with real vigor, and any matter falling toward it, any light grazing past it, is swept up in that swirl to a degree that would be utterly impossible near a slowly turning planet. To appreciate just how different the environment near such an object is, picture light itself trying to make its way past a rapidly spinning neutron star. Around our slowly turning Earth, the frame dragging is so feeble that a beam of light is bent and twisted by an utterly negligible amount, far too little to notice. But near the surface of a neutron star spinning hundreds of times a second, the dragged geometry is fierce enough that light passing by is noticeably swept along in the direction of the spin. A ray that approaches the star moving against the rotation finds its path bent one way, while a ray approaching with the rotation is bent differently, the swirling geometry treating the two directions of travel as fundamentally distinct. The very paths that light can take are skewed by the rotation, the symmetry that would exist around a still star broken open by the spin. This is the same effect that barely registers around the Earth, grown into something that genuinely sculpts the paths of light grazing the star. The same goes for any matter falling towards such a star. Around a non-rotating object, infalling matter would trace a path determined purely by the inward pull, with no preference for one rotational direction over another. But around a fast-spinning neutron star, matter spiraling inward is caught in the dragged geometry and swept around in the direction of the spin as it falls, its path curving not just inward but around, carried along by the twist in space-time. The matter is not being touched, not being pushed by any wind or current. It is following its straightest available path, the only path the geometry leaves open to it. It is only that those straightest paths, near a furiously rotating mass, have acquired a pronounced swirl. And because neutron stars often possess intense magnetic fields and are surrounded by infalling material, the interplay between the dragged geometry and that material can imprint subtle signatures on the radiation we receive, offering, in principle, another window onto the rotation of these objects. The whisper that the Earth produces has, near a neutron star, swelled into a force that visibly bends light and curves the fall of matter, a clear step on the climb toward the most extreme dragging the universe can offer. But neutron stars, extreme as they are not the ultimate stage for frame dragging. For that, we have to turn to the most concentrated, most extreme objects gravity can produce. The objects where matter has collapsed so completely that nothing, not even light, can escape from a certain region around them. We have to turn to black holes. And here we encounter one of the most beautiful and important ideas in the whole subject, because the geometry of a spinning black hole is fundamentally different from the geometry of one that does not spin. And understanding that difference is the key to seeing frame dragging in its most powerful form. Let us start with the simpler case, a black hole that does not rotate at all. The geometry of space-time around a perfectly still, non-rotating black hole was worked out very early in the history of Einstein's theory by a physicist named Schwarzschild, who solved Einstein's equations for the simplest possible case of a spherical mass that just sits there. The Schwarzschild geometry describes a clean, symmetric warping of space-time, exactly the kind of inward-pulling dimple we discussed at the very beginning, but taken to its ultimate extreme. There is a boundary around the black hole called the event horizon, and it is the point of no return. Cross it, and you can never come back, because escaping would require moving faster than light, which nothing can do. Inside, all paths lead inexorably inward. Outside, you can still escape if you move fast enough or thrust hard enough. The Schwarzschild geometry is the geometry of a black hole with no spin, and, like the stationary planet we discussed earlier, it has no swirl to it whatsoever. It pulls inward symmetrically, the same in every direction around the hole. There is no preferred sense of rotation, no twist, no dragging of frames, because there is no angular momentum to produce one. It is the purest possible inward dimple, but a dimple so deep it has become a one-way door. Now let the black hole spin, and everything changes. A rotating black hole is not described by the Schwarzschild geometry at all. It is described by a different solution to Einstein's equations, found decades later by a mathematician named Kerr, and the Kerr geometry is one of the crown jewels of the entire theory. What Kerr discovered is the exact shape of space-time around a mass that has collapsed into a black hole while carrying angular momentum, while spinning. And the Kerr geometry contains everything the Schwarzschild geometry has: the event horizon, the one-way door, the deep inward pull. But it adds to all of that the swirl, the twist, the frame dragging, woven into the very structure of space and time around the hole. The black hole's rotation is not stored in some spinning surface or churning material. A black hole has no solid surface to rub against space. Its angular momentum is encoded directly in the geometry itself, in the Kerr solution, in the way the shape of space-time differs from the stationary Schwarzschild case. The spin of the black hole is written into the curvature and the twist of the surrounding region, and that is the only place it lives. There is nothing there but geometry, and the geometry carries the rotation. This is worth pausing on because it is genuinely profound. When we say a black hole spins, we are not picturing a ball turning on its axis, because there is no ball, no surface, nothing material to turn. The black hole is a region of space-time so severely warped that it has closed off from the rest of the universe. What we mean by its spin is entirely captured by the angular momentum imprinted in the Kerr geometry around it. The rotation is a property of the shape of space and time, not of any substance. And that imprinted rotation is exactly what produces the frame dragging, the swirl that grabs nearby matter and carries it around. The faster the black hole spins, the more extreme the angular momentum, the more violently the Kerr geometry twists, and the more powerfully it drags everything near it. So what does this swirl actually do to matter around a spinning black hole? Here is where one of the most striking consequences emerges, and it follows directly from everything we have built. Imagine matter orbiting a rotating black hole. Now imagine two different streams of matter, one orbiting in the same direction the black hole spins, and one orbiting in the opposite direction. In ordinary gravity, around a non-spinning mass, the direction you orbit makes no difference. An orbit clockwise and an orbit counterclockwise at the same distance behave identically. because the geometry has no preferred sense of rotation. But around a spinning black hole, the direction matters enormously, because the geometry itself is twisting. Matter that orbits in the same direction as the black hole's spin is called prograde, moving with the swirl. Matter that orbits against the spin is called retrograde, fighting the swirl. And because the frame dragging carries the local frames around in the direction of the spin, these two cases are no longer equivalent. They experience the dragged geometry differently, and the difference shapes where they can orbit and how stable those orbits are. Think about it this way. The frame dragging is trying to sweep everything around in the direction of the black hole's rotation. If you are orbiting prograde with the spin, the dragging is, in a sense, helping you along, working in concert with your motion. If you are orbiting retrograde against the spin, the dragging is constantly working against you, fighting your direction of travel. The result is that prograde and retrograde orbits have different allowed radii. There is an innermost, stable orbit, a closest distance at which matter can circle the black hole without spiraling in, and that innermost stable orbit sits at a different radius depending on which way you go. For matter moving with the spin, prograde, the innermost stable orbit can lie much closer to the black hole, because the dragging assists the motion and allows stable circling at smaller distances. For matter moving against the spin, retrograde, the innermost stable orbit sits farther out, because fighting the dragging makes close orbits unstable, sending matter plunging inward sooner. The same black hole, the same distance, and yet whether you can hold a stable orbit there depends entirely on which direction you travel, a direct and dramatic consequence of the geometry having been set spinning. It helps to think about why the dragging assists one direction and fights the other, because the physical picture is clearer than the equations suggest. Imagine you are matter trying to hold a stable circular orbit close to the spinning hole. To stay in orbit at a given distance, you need to be moving at a particular speed, fast enough that you do not spiral inward, but in balance with the geometry around you. Now the frame dragging is constantly carrying the local frames around in the direction of the spin. If you are orbiting prograde, moving with that swirl, then the dragging is already carrying you partway around in the direction you wish to go. You are, in effect, getting a head start from the geometry itself. The swirl does some of the work of keeping you in orbit, and so you can maintain a stable orbit even quite close to the hole, where the dragging is strongest. The closer you go, the more the dragging helps, and prograde matter can therefore circle stably at distances that would be utterly forbidden around a non-spinning hole. If instead you are orbiting retrograde, moving against the swirl, the situation reverses. Now the dragged geometry is constantly trying to carry you backward, against your direction of travel. You are fighting the current of the geometry the entire way around. The swirl works against your orbit rather than supporting it, and this makes close orbits precarious. The geometry that would have stabilized a prograde orbit now destabilizes a retrograde one, so the closest distance at which you can hold a stable retrograde orbit lies considerably farther out. Venture any closer while moving against the spin, and the dragging overwhelms your orbit and sends you plunging inward. So the very same point in space, the very same distance from the hole, can be a perfectly stable orbit for matter traveling one way and an impossible, unstable position for matter traveling the other. The geometry has acquired a handedness, a built-in sense of which way is favored, and that handedness comes entirely from the angular momentum of the spinning hole imprinting its swirl into the surrounding space-time. There is no clearer demonstration that the geometry itself is twisting than this, that the universe near a spinning black hole genuinely cares which direction you choose to orbit. I want to be careful here not to drown us in orbital mathematics, because the equations governing these orbits are genuinely intricate, and the precise radii depend in complicated ways on how fast the black hole spins. The point I want to leave you with is not the formulas, but the physical mechanism. The reason prograde and retrograde orbits differ is that the space-time itself has a swirl, a directional twist inherited from the black hole's angular momentum, and matter moving with that swirl finds a different landscape than matter moving against it. The geometry is no longer indifferent to direction. It has a handedness, a sense of rotation built into it, and that handedness reaches out and shapes the paths available to everything nearby. This is frame dragging operating at full strength, no longer a subtle correction, but a force powerful enough to completely reshape where matter can and cannot orbit. Now we arrive at one of the most remarkable features of a spinning black hole, a feature that exists only because of frame dragging, and that has no counterpart at all around a non-spinning hole. It is called the ergosphere, and it is a region where the dragging of space-time becomes so overwhelming that something genuinely impossible begins to happen. To understand it, let us return to the idea of standing still. Near any massive object, you can, in principle, hold your position if you have a powerful enough rocket. Fire your engines hard enough against the inward pull, and you can hover at a fixed point, watching the distant stars hold steady around you. Even just outside the event horizon of a non-spinning black hole, with a sufficiently mighty rocket, you could, in principle, hold station, remaining at a fixed point relative to the distant stars, fighting the inward pull, but staying put in your angular position, not being swept around. Around a spinning black hole, there is a region where this becomes flatly impossible, and that region is the ergosphere. It lies outside the event horizon, in the space surrounding the spinning hole, and it is defined by exactly this property. Within the ergosphere, the frame dragging is so intense that no amount of rocket thrust, no power source imaginable, can keep you stationary relative to the distant stars. The dragging of the local frames is so powerful that it exceeds the speed of light for anything trying to hold still against it. To remain motionless relative to the distant stars, you would have to move faster than light through the local geometry, and that is something nothing can do. So instead, everything inside the ergosphere is forced to rotate, carried around in the direction of the black hole's spin, whether it wants to or not. You can fire your rockets as hard as you like, point them however you wish, and you will still be swept around in the direction of the spin. Standing still, in the sense of holding your angular position against the rotation, has become physically impossible. The local definition of holding still has been dragged so far around that no object can keep pace with the distant stars. The swirl wins. I have to immediately guard against a misconception here, because it is a tempting and wrong conclusion. The fact that you cannot hold still inside the ergosphere does not mean you are trapped, and it does not mean you must fall into the black hole. This is a crucial distinction, and getting it wrong leads to a badly mistaken picture. The ergosphere is not a region of no return. You can still move within it. You can still travel inward or outward. And given suitable circumstances, you can escape from the ergosphere entirely and fly back out into the wider universe. The one thing you cannot do is remain stationary relative to the distant stars while you are inside it. You are forced to share in the rotation, forced to be carried around in the direction of the spin, but you are not forced to fall in. You can be swept around and still climb back out. Matter can enter the ergosphere, be dragged around by the swirling geometry, and then leave again, having been turned but not captured. The ergosphere compels rotation, not capture. And this brings us to perhaps the most important conceptual point in this entire region of the discussion. Being forced to rotate inside the ergosphere does not mean the matter is mechanically attached to the black hole. Nothing is gripping the matter. Nothing is holding onto it and spinning it around like a child on a carousel clutching the bar. There is no connection, no contact, no rope, no rubbing surface. The compulsion to rotate comes entirely from the geometry. Inside the ergosphere, the space-time is dragged around so completely that every possible path an object can take into its own future shares some motion in the direction of the spin. Let me say that again, because it is the heart of the matter. Every future-directed path, every way that matter or light can possibly move forward in time, necessarily includes some component of motion in the direction the black hole is rotating. There is simply no available path that holds still. The geometry has been twisted to the point where standing still is not among the options the universe offers. So the matter rotates, not because it is held, but because every direction it could move toward the future is a direction that carries it around with the spin. It is following its straightest possible path through the geometry, just as a falling apple does, just as an orbiting moon does. It is only that, in here, all the straightest possible paths swirl in the same direction, and none of them stand still. This is frame dragging in its most absolute form. Out near the Earth, the dragging was a faint nudge, deflecting a perfect gyroscope by a few milliarcseconds a year. Here, in the ergosphere of a rapidly spinning black hole, the dragging is so total that it removes the very possibility of holding still. The same phenomenon, the same twisting of geometry by angular momentum, spans this entire range, from the gentlest whisper to a swirl so commanding that it rewrites what motions are even available to matter. And throughout that range, the mechanism never changes. Rotation reshapes the geometry, and matter follows the reshaped geometry, with nothing touching it at any point. Let me draw the distinction between the ergosphere and the event horizon as sharply as I can, because confusing them is one of the most common errors, and the difference illuminates everything. The event horizon is the true boundary of no return. Cross it, and escape becomes impossible, because every future-directed path leads inward, toward the center, with no way out. The event horizon is about capture, about the point beyond which nothing can ever come back. The ergosphere is something else entirely. It lies outside the event horizon, surrounding it, and it is about compulsion to rotate, not about capture. Within the ergosphere, you cannot hold still, but you can still escape. Within the event horizon, you cannot escape at all. The two boundaries are nested, the ergosphere on the outside, the event horizon within it, and they mark two completely different thresholds. One marks where standing still becomes impossible. The other marks where leaving becomes impossible. For a spinning black hole, these two surfaces touch at the poles, along the axis of rotation, but bulge apart around the equator, where the dragging is strongest, leaving a region between them, the ergosphere proper, where you are forced to rotate, but not yet forced to fall. And here is a point I cannot stress enough, because it corrects a misconception that lurks even in many casual descriptions. Frame dragging is not confined to the ergosphere. The ergosphere is merely the region where the dragging becomes so extreme that holding still is impossible. But the dragging itself extends far beyond the ergosphere, far beyond the event horizon, reaching out into the surrounding space and fading only gradually with distance, exactly as it does around the Earth, around a neutron star, around any rotating mass. A gyroscope placed well outside the ergosphere, well outside the event horizon, in the ordinary space around a spinning black hole, will still process, still be dragged, still feel the swirl, just less intensely than it would closer in. The ergosphere is not where frame dragging happens. It is simply where frame dragging reaches the extreme of forbidding stillness. The effect is everywhere around the spinning hole, strongest near the surface and weakening outward, just a vastly amplified version of the same gentle twist the Earth produces. To think frame dragging lives only inside the ergosphere would be like thinking gravity lives only at the surface of a planet. The truth is that it pervades all the surrounding space, with the ergosphere marking just one special threshold within that broader field of swirling geometry. Now let us connect this powerful dragging to things we can actually observe, because spinning black holes are not just theoretical curiosities. They sit at the centers of galaxies and at the hearts of certain binary star systems. and they are often surrounded by matter. When gas and dust fall toward a black hole, they rarely fall straight in. Instead, because of their own angular momentum, they swirl into a flattened, rotating disk circling the hole, called an accretion disk. This disk of infalling matter spirals inward, heating to tremendous temperatures through friction and compression, glowing brilliantly across the spectrum, and it is one of the main ways we detect black holes at all, by the light pouring off this swirling, superheated material. And the frame dragging of the spinning black hole reaches out and influences this disk in ways we can study. The twisting of spacetime can affect how the inner regions of an accretion disk orbit, since, as we discussed, the innermost stable orbit depends on whether the matter is prograde or retrograde, and on how fast the hole spins. This means the inner edge of the disk, the closest the glowing matter can stably circle, is shaped directly by the black hole's spin and the frame dragging it produces. By studying the light from these inner regions, the way it is shifted and distorted as it climbs out of the deep gravity and battles the swirling geometry, astronomers can attempt to infer how fast the black hole is spinning. The frame dragging leaves its fingerprint on the radiation, and reading that fingerprint is one of the ways we probe the rotation of these otherwise invisible objects. There is another beautiful consequence. If the accretion disk is tilted, not aligned with the black hole's equator, the frame dragging can cause the inner part of the disk to slowly precess, to wobble around, twisted by the dragged geometry. The inner region, closest to the hole where the dragging is fiercest, gets pulled toward alignment with the spin and set into a slow precession, while the outer regions, farther out where the dragging is weaker, lag behind. This can produce twisted, warped shapes in accretion flows, and it can cause the light from these inner regions to vary in regular, repeating patterns as the precessing matter sweeps around. Some of the flickering and periodic variation astronomers observe in the light from black hole systems may be connected to exactly this kind of frame-dragging-induced precession of the inner accretion flow, a direct astrophysical signature of space-time being twisted by rotation. I want to add a careful caveat here, because it is easy to overreach with black holes, and intellectual honesty demands restraint. Spinning black holes are often associated with spectacular jets, enormous beams of matter and energy blasting out from their poles at nearly the speed of light, reaching across vast distances. It is tempting to say that frame dragging alone explains these jets, but that would be an overstatement. The launching of these jets is a complicated affair, involving not just the twisted geometry, but also powerful magnetic fields threading the accretion disk and the region around the black hole. Fields that get wound up and channeled in intricate ways. Frame dragging very likely plays an important role, helping to twist and organize the magnetic fields and the flow of matter near the spinning hole, but it is not the whole story by itself. The jets emerge from a collaboration between the dragged geometry and the magnetic environment, and we should resist the temptation to credit frame dragging with the entire phenomenon. It is a crucial ingredient, but only one of several, and the full picture remains an active area of research. It could easily swallow our whole discussion if we let it. The rotation of a black hole represents a genuine store of energy. Energy bound up in the spin itself, encoded in the Kerr geometry. And in principle, that rotational energy can be extracted. The ergosphere, that region where matter is forced to rotate but can still escape, turns out to be the key. Because matter can enter the ergosphere, be acted upon by the swirling geometry, and then leave again, it is possible, under the right circumstances, for matter to exit carrying away more energy than it brought in, with the difference drawn from the black hole's rotational energy, slowing the hole's spin very slightly in the process. There are also mechanisms involving the magnetic fields threading the region, where the rotational energy of the black hole can be tapped through the twisting of those fields by the dragged geometry, channeling enormous power outward. I mention these only to show that the swirling of space-time is not merely a passive curiosity, but can have real energetic consequences, that a spinning black hole is, in a sense, a vast reservoir of rotational energy that the twisted geometry makes accessible. But I will not let these energy extraction mechanisms become a separate story of their own, because they are secondary to our central theme. What matters for us is the underlying picture they all share. In every one of these cases, the spinning black hole influences the matter and fields and light around it, not by touching them, not by gripping them, but through the swirling geometry of space-time, the Kerr geometry, with its frame dragging woven into every point of the surrounding space. There is one more consequence of all this swirling geometry that deserves a closer look, because it reveals that the rotation of a black hole is not merely a curiosity of shape, but a genuine reservoir of usable energy. The spin of a black hole, encoded in the Kerr geometry, represents a real store of energy, energy bound up in the rotation itself. And remarkably, that rotational energy can in principle be extracted, drawn out of the black hole and carried away, with the ergosphere serving as the stage on which this becomes possible. To see how, we have to return to that strange property of the ergosphere, the fact that matter can enter it, be acted upon by the dragged geometry, and then escape again, carried around but not captured. Imagine a piece of matter sent into the ergosphere from outside. Once inside, recall, it cannot hold still. It is forced to share in the rotation, swept around in the direction of the spin by the twisted geometry. Now suppose that while it is inside the ergosphere, this piece of matter splits into two parts. One part is directed so that it falls inward, toward the event horizon, while the other part is flung back outward, escaping the ergosphere and returning to the wider universe. Here is the remarkable thing. Because of the peculiar nature of the geometry inside the ergosphere, the part that falls into the hole can carry what amounts to negative energy, as measured from far away. Energy that, when swallowed, actually reduces the total energy and the spin of the black hole. And by the accounting the geometry enforces, the part that escapes can carry away more energy than the original piece brought in. The surplus is not created from nothing. It is drawn directly from the rotational energy of the black hole, which slows its spin by a tiny amount in the exchange. Matter goes in. Matter comes out richer in energy than it entered, and the difference is paid for out of the hole's rotation. This is a genuinely astonishing prospect. It means a spinning black hole is, in effect, a vast flywheel, storing colossal amounts of energy in its rotation, energy that the geometry of the ergosphere makes accessible to anything clever enough, or fortunate enough, to exploit it. There is also a second route to tapping this rotational energy, one that involves magnetic fields rather than splitting matter. If magnetic field lines thread the region around the spinning hole, the dragged geometry of the ergosphere can wind those field lines up, twisting them as it carries the local frames around, and this twisting can channel the black hole's rotational energy outward along the field lines, flinging energy and matter away from the poles in powerful streams. In both cases, whether through the splitting of matter or the winding of magnetic fields, the underlying source is the same. It is the rotational energy of the black hole, made available by the frame dragging woven into the ergosphere, drawn out without anything ever reaching in and touching the hole. I want to keep these energy extraction processes in their proper place, secondary to our central theme, rather than a separate story unto themselves, because it would be easy to let them run away with the discussion. But they matter for our purposes because of what they reveal about the nature of the swirling geometry. They show that the dragging of space-time is not a passive, ornamental feature, not merely an interesting wrinkle in the shape of things. It is dynamically real enough to carry energy, slow a black hole's spin, and power some of the most energetic outflows in the universe. And in every one of these processes, the spinning black hole influences the matter and fields and energy around it, not by touching them, not by gripping them with any surface or hand, but through the swirling geometry of space-time, the Kerr geometry, with its frame dragging woven into every point of the surrounding space. The energy flows outward, the spin winds down, and yet nothing has ever made contact. The geometry alone does all the work, exactly as it does everywhere else in this story, only here with consequences energetic enough to light up across a galaxy. So, step back and survey what we have found. We began with frame dragging as a faint whisper around our slowly turning planet, barely detectable with the most perfect instruments ever built. And now we have followed it to its most extreme expression, around objects where rotation has been concentrated and amplified beyond all everyday experience. Around a fast-spinning neutron star, the dragging becomes a substantial, undeniable twisting of the surrounding geometry. Around a rotating black hole, described not by the simple Schwarzschild geometry, but by the richer Kerr geometry, the dragging reshapes the very orbits matter can occupy, making prograde and retrograde paths fundamentally different. And it creates the ergosphere, a region where holding still is no longer among the options the universe permits, where every path into the future swirls in the direction of the spin. And throughout it all, the mechanism has never wavered. Angular momentum imprints a swirl into the geometry of space-time. Matter, light, and gyroscopes follow that swirling geometry. Nothing is ever touched. The black hole has no surface to rub against space, no hand to grip the matter, no rope to pull it around. There is only the shape of space and time, twisted by rotation, guiding everything nearby along paths that carry them, partway or wholly, around with the spin. And yet, even now, with all of this laid out, the deepest misconceptions still need to be confronted directly. We have spoken of space-time being dragged, of geometry swirling, of frames being carried around. And these phrases, powerful as they are, hide a danger. They tempt us to imagine space-time as a kind of cosmic fluid, a whirlpool of some invisible substance churning around the spinning mass and sweeping matter along by contact after all. That picture is wrong, and dismantling it completely, understanding what it truly means to drag matter without touching it, is exactly where we must turn to finish our journey. We have reached the point where we must dismantle, carefully and completely, the most seductive misconception in this entire subject. Throughout our journey, we have used words like swirl, twist, drag, and carried around, and these words have done honest work for us. But they carry a hidden poison, because they tempt the mind toward a picture that is fundamentally false. When you hear that a spinning mass drags space-time, that the geometry swirls around a rotating black hole, that matter is carried partway around with the rotation, it is almost irresistible to imagine that space-time is a kind of substance, an invisible fluid filling the universe, and that the spinning mass stirs this fluid like a spoon stirring coffee, setting up a whirlpool that sweeps nearby matter along in its current. This image feels intuitive. It seems to explain everything. And it is wrong. Let me be as direct as I can be. Space-time is not a fluid. It is not a solid. It is not a substance of any kind that physically rotates around the object, like water circling a drain. There is no cosmic material being stirred, no medium with currents and eddies, no invisible whirlpool of stuff churning around the spinning mass. When we say the geometry swirls, we do not mean that something is moving in circles. The swirl is not a swirl of material. The swirl is a property of the geometry itself, of the relationships between points in space and moments in time, of which directions count as standing still and which count as turning. There is nothing there to spin in the ordinary sense, because space-time is not made of stuff that could spin. What rotates, if we must use that word, is the very structure that defines motion and rest, not any material occupying that structure. So what does it really mean, then, that rotating space-time drags matter? It means precisely this, and I want to state it with full clarity, because everything we have built leads to this single point. The angular momentum of the rotating mass alters the geometry of the surrounding region. That altered geometry changes which local directions count as non-rotating, changes the definition of holding still, changes the straightest available paths through space and time. And matter, light, clocks, and gyroscopes do nothing more than follow those straightest available paths, exactly as they always do, exactly as a falling apple follows its geodesic toward the earth. The reason they acquire a swirling motion is not that they are pushed by a current, not that they are gripped by a rotating substance, but that the paths themselves, the geodesics, now carry a twist, because the geometry that defines them has been reshaped by the rotation. The matter is following the path of least resistance, the most natural path available, the path that requires no force at all. It is just that this path now spirals in the direction of the spin, because the rotation has carried the meaning of straightness around with it. This is the resolution to the entire paradox of the title. Rotating space-time drags matter without touching it, because there is no touching anywhere in gravity. Not for a spinning mass, and not for a stationary one. Gravity, in Einstein's universe, never works by touching. It never works by pushing or pulling through contact. It works by shaping the geometry through which things move, and things respond to that geometry by following their straightest paths. A stationary planet shapes the geometry into an inward dimple, and matter follows paths that lead inward, and we call that falling. A rotating mass shapes the geometry into an inward dimple with a swirl added, and matter follows paths that lead inward and around, and we call that frame dragging. In neither case is anything touched. In neither case is there a current of substance carrying matter along. There is only geometry, and matter faithfully tracing the straightest lines that geometry allows. The whisper that nudges a gyroscope in orbit around the Earth, and the swirl that forbids stillness inside a black hole's ergosphere, are the same phenomenon. Geometry reshaped by rotation, matter following the reshaped geometry. No contact anywhere to be found. Now, there is a powerful and illuminating analogy that physicists reach for to make sense of frame dragging, and, used carefully, it can deepen our understanding enormously. But used carelessly, it can plunge us right back into the fluid misconception. So, I want to introduce it with great caution. The analogy is with electromagnetism. You are familiar, in broad strokes, with how electricity and magnetism work. A stationary electric charge produces an electric field around it, reaching out and influencing other charges. But a moving charge, a charge in motion, produces something additional, a magnetic field. And a current of moving charges, flowing in a loop, produces a magnetic field with a particular structure, the kind you find around an electromagnet or a bar magnet. The crucial point is that motion of charge produces a new kind of effect, the magnetic effect, that a stationary charge does not produce. Gravity, it turns out, has a mathematical structure remarkably similar to this. A stationary mass produces what we might call the ordinary gravitational effect, the inward pull, analogous to the electric field of a stationary charge. But a moving mass, and especially a rotating distribution of mass, produces something additional, an effect mathematically reminiscent of the magnetic field produced by moving charges. Physicists call this additional effect gravitomagnetism, and frame dragging is precisely its consequence. Just as moving charges create magnetism, moving and rotating mass energy creates this gravitomagnetic effect, this twisting of the geometry that drags frames around. The mathematics of the two situations, in the regime of weak gravity, runs startlingly parallel. The way a spinning mass drags spacetime echoes in its equations the way a spinning charge or a current loop creates a magnetic field. This is a deep and genuine correspondence, and it is one of the reasons frame dragging was anticipated mathematically long before it could be measured. But I must now place the warnings around this analogy as firmly as I can, because the analogy, for all its power, can mislead in two serious ways. The first warning is this: gravitomagnetism is not ordinary magnetism. It has nothing to do with magnets in the everyday sense. It does not require any electric charge whatsoever. A completely uncharged, unmagnetized mass, a perfectly neutral lump of matter with no electrical properties at all, still produces this effect when it rotates. The Earth drags space-time not because of any magnetism in the usual sense, but simply because it is a rotating mass. The word gravitomagnetism borrows the term magnetism only because the mathematics resembles the mathematics of magnetism, not because any actual magnetic field is involved. Do not imagine that the spinning mass creates a literal magnetic field, because it does not. It creates a gravitational effect that happens to be described by equations of a similar form. The resemblance is in the mathematics, in the structure of the relationships, not in the physical nature of the thing. Frame dragging is gravity, purely and entirely, dressed in equations that rhyme with those of magnetism. The second warning about the analogy returns us to our central theme. The electromagnetic analogy, helpful as it is, must never be allowed to resurrect the idea of a force acting from a distance, or of a substance being stirred. Frame dragging does not supply a conventional force that reaches across space to push matter around. It is not a gravitomagnetic force in the sense of a hand reaching out and shoving. It is, like all of gravity in Einstein's theory, a matter of geometry, of matter following geodesics through curved and twisted spacetime. The gravitomagnetic language is a useful way to organize the mathematics, a useful way to see the parallel with electromagnetism. But underneath it all, the truth remains that there is no force, no push, no current of substance. There is only the altered geometry and the matter following its straightest paths through that geometry. The analogy is a ladder we climb to gain intuition, and then, having climbed it, we must remember that the real picture is geometric, not a matter of forces or fields stirring an invisible medium. So let us be completely precise about what the title's phrase "without touching it" really means, because this is the conceptual heart of everything. When we say a rotating mass drags matter without touching it, we are making a very specific claim, and it is easy to misread. We are not claiming that there is no interaction between the rotating mass and the nearby matter. There absolutely is an interaction. The rotating mass and the nearby matter are interacting, and interacting quite genuinely through gravity, through the geometry of space-time. The matter feels the influence of the spinning mass, responds to it, has its motion shaped by it. That is a real, physical interaction, as real as any in nature. What without touching means is something narrower and more precise. It means there is no contact force at work, nothing mechanical bridging the gap, no surface pressing on the matter, and no medium physically pushing against it. The interaction is not of the kind we experience when one object touches another, when a hand pushes a ball or a wind pushes a sail. It is gravitational, mediated by the shape of space-time, and gravity in Einstein's theory simply does not work by contact. So the matter is interacting with the rotating mass, profoundly and genuinely, but it is not being touched by it. The absence is the absence of a contact force, not the absence of interaction. These are completely different things, and conflating them is the root of much confusion. To say nothing touches the matter is not to say nothing affects it. The geometry affects it intimately. It simply does so without contact. There is another subtle point we must address to keep our picture honest, and it concerns the speed at which all of this happens. It would be easy, having absorbed everything so far, to imagine that a spinning mass instantly reaches out and grabs the geometry everywhere around it. That the moment a mass begins to rotate, the entire surrounding space-time is twisted at once, no matter how far away. But this is not how it works, and Einstein's theory is very clear on the point. Changes in the gravitational field do not propagate instantaneously. They travel at a finite speed, the speed of light, the ultimate speed limit woven into the structure of space-time itself. If a mass were suddenly to begin rotating, or to change its rotation, the alteration in the surrounding geometry would not appear everywhere at once. It would spread outward from the mass at the speed of light, reaching nearby regions first and distant regions only later, ripple by ripple, never faster than light can travel. The frame dragging around a steadily spinning mass that has been spinning for a long time is a settled, established feature of the geometry. But any change to it respects the cosmic speed limit, propagating outward at the speed of light and no faster. This matters enormously because it guards against another tempting misconception, the idea that frame dragging might be some kind of faster-than-light influence, some instantaneous reaching across space. It is not. Nothing about frame dragging violates the speed limit. The dragging is a property of the geometry, and the geometry, when it changes at the speed of light. A rotating mass does not instantly twist space-time across the entire universe. It twists the geometry around it, and that twist is communicated outward at the finite speed that relativity permits. The matter that responds to the swirling geometry is responding to the geometry as it is right there, locally, and that local geometry was shaped by influences that travel to it at the speed of light. There is no spooky, instantaneous action, no faster-than-light grabbing. Everything respects the structure of space-time, including the speed at which gravitational influence can travel. Frame dragging is a local phenomenon, matter responding to the geometry in its own neighborhood, and the establishment of that geometry obeys the same speed limit that governs everything else in the universe. Now I want to step back and ask why Newtonian gravity, the older picture of gravity as a force, does not naturally contain anything like frame dragging, because this comparison reveals just how special and how deeply geometric the effect really is. In Newton's picture, gravity is a force that depends only on mass and distance. The pull between two objects depends on how much mass they have and how far apart they are, and that is all. There is nothing in Newton's law about rotation. A spinning mass and a non-spinning mass of the same total amount produce exactly the same gravitational pull, according to Newton, because the pull depends only on the mass, not on whether or how it is turning. In the Newtonian world, rotation simply does not enter into gravity at all. A spinning ball and a still ball of the same mass tug on you identically. There is no mechanism in Newton's framework for the rotation of a mass to influence the motion or orientation of distant objects, no place for angular momentum to leave any gravitational imprint. Newtonian gravity is, in this sense, blind to rotation. This is why frame dragging is such a striking and distinctive prediction of Einstein's theory, and not of Newton's. It exists precisely because Einstein replaced the idea of gravity as a simple force depending only on mass, with the far richer idea of gravity as the geometry of space-time, a geometry that responds not just to how much mass and energy is present, but to how that mass and energy is moving, including how it is rotating. In Einstein's theory, the full state of motion of the matter matters, not just its quantity. A rotating distribution of mass-energy shapes the geometry differently from a stationary one, and that difference is the frame dragging. Newton's gravity, depending only on mass and distance, has no room for this. It is a consequence that emerges only when you take the geometric view seriously, only when you understand gravity as the shape of space and time rather than as a force reaching between objects. Frame dragging is, in a sense, a signature of the geometric nature of gravity, a phenomenon that simply cannot exist in a world where gravity is merely a pull depending on mass alone. Its very existence is testimony that Einstein's picture, not Newton's, is the deeper truth. Let us also be honest and careful about how we know all of this, because intellectual integrity demands that we distinguish what has been directly measured from what has been inferred. Frame dragging is a firm prediction of general relativity, flowing inevitably from the equations the moment you allow a mass to rotate, and it has been tested observationally, which is a remarkable achievement given how tiny the effect is around accessible objects. The most direct tests involve the kind of careful gyroscope and satellite measurements we discussed earlier, where the slow precession of gyroscopes in orbit around the Earth, or the gradual shift of satellite orbits caused by the same twist in the geometry, has been measured and found consistent with what the theory predicts. These are genuine experimental confirmations conducted in our own backyard around our own spinning planet with instruments of extraordinary precision. They tell us that frame dragging is real, that the Earth really does drag space-time by roughly the amount Einstein's equations demand. But I want to draw a clear line between these direct measurements and the astrophysical inferences we make about black holes and neutron stars. When astronomers study the light from accretion disks around black holes, or the variations in that light, or the shapes of jets, and conclude that frame dragging is at work, they are making inferences, interpreting observations through the lens of the theory. These inferences are reasonable, often compelling, and consistent with the framework, but they are not the same as the direct, controlled measurement of a gyroscope's precession in Earth orbit. The astrophysical environment around a black hole is complicated, full of hot gas and magnetic fields and turbulent flows, and disentangling the precise role of frame dragging from everything else is genuinely difficult. So, while these observations support the picture, while they are consistent with strong frame dragging around spinning compact objects, we should be careful not to overstate their precision or treat any single astrophysical observation as a clean, conclusive measurement of the effect. The direct confirmation comes from the careful local experiments. The astrophysical observations show us the effect operating in the extreme regimes where it becomes dominant, but they do so through inference and interpretation rather than through the kind of controlled precision that gyroscopes in Earth orbit provide. Both kinds of evidence matter, and together they build confidence, but they are different in character, and honesty requires us to keep that difference in view. So now, having dismantled the misconceptions and drawn all the careful distinctions, let us gather the full picture together and return, finally, to the question that has guided us from the very beginning. How can rotating space-time drag matter without touching it? We are now in a position to answer this completely, with no hand-waving and no mystery left unexplained. The answer begins with the recognition that gravity, in its deepest nature, is not a force at all. It is the geometry of space and time. Mass and energy curve and shape that geometry, and everything that moves through it follows the straightest available paths, the geodesics, requiring no force and feeling no push. A stationary mass shapes the geometry into an inward warp, and matter follows paths that lead inward, which we experience as falling, as weight, as the familiar pull of gravity. But a rotating mass does something more. Its angular momentum, that combined measure of how much mass it has, how fast it spins, and how widely that mass is distributed, imprints an additional feature into the geometry, a swirl, a twist, a directional sense of rotation that a stationary mass cannot produce. This swirl changes which local directions count as non-rotating. It carries the very definition of holding still around in the direction of the spin, and matter, light, clocks and gyroscopes, doing nothing more than following their straightest available paths through this twisted geometry, are carried partway around with the rotation. They are not pushed, they are not gripped, they are not stirred by any current of substance. They are simply tracing the most natural paths available, paths that now spiral in the direction of the spin because the geometry that defines them has been reshaped. This is why the phrase "without touching" is both true and not as paradoxical as it first sounds. There is no contact force anywhere in this process. No mechanical connection, no rubbing, no rope, no whirlpool of material sweeping matter along. Gravity never works by contact, for a spinning mass no more than for a stationary one. But there is most certainly an interaction, a profound and genuine gravitational interaction, mediated entirely by the geometry of space-time. The rotating mass shapes the geometry, and the matter responds to that geometry, and that response is the dragging. The matter and the mass are interacting through the shared structure of space and time, intimately and continuously, without ever touching, because the medium of their interaction is geometry itself. We have seen this single mechanism span an extraordinary range. Around our own slowly turning planet, it is a whisper so faint that detecting it required gyroscopes polished to a perfection beyond almost anything humanity has ever built, drifting them off a distant star by only a few milli-arcseconds across an entire year. Around a fast-spinning neutron star, it becomes a substantial twisting of the surrounding geometry. And around a rotating black hole, described by the rich Kerr geometry rather than the simpler Schwarzschild geometry of a non-spinning hole, it grows so powerful that it reshapes the very orbits matter can occupy, making the path of matter moving with the spin fundamentally different from the path of matter moving against it, and creating the ergosphere, that remarkable region outside the event horizon where holding still relative to the distant stars becomes flatly impossible, where every path into the future shares some motion in the direction of the spin, yet from which matter can still escape, carried around but not captured, compelled to rotate yet never mechanically held. Through this entire vast range, from whisper to roar, the mechanism never changes. Rotation imprints a swirl into the geometry. Matter follows the swirling geometry. Nothing is touched. And so we arrive at last at the deepest meaning of everything we have explored, the idea I most want you to carry with you. We tend to think of rotation as something an object does within space, a spinning that takes place against a fixed and unchanging backdrop, the way a top spins on a table while the room stays still around it. But Einstein's universe teaches us something far stranger and far more beautiful. Rotation does not merely move an object through a passive, unaffected space. A rotating mass helps to determine the structure of the space and time around it. The spinning is not contained within an indifferent stage. The spinning reaches into the stage itself, into the geometry, into the very definition of which directions count as turning and which count as still. And it carries that geometry partway around. The local frames, the local sense of rest, the straightest paths available to all nearby matter, are all shaped by the rotation. The spinning mass does not just turn within space and time, it turns space and time in the precise sense that it reshapes the geometry that governs all motion and orientation around it. This is why rotating space-time can drag matter without touching it. Because general relativity does not require gravity to act as a conventional push or pull, reaching across space to grab hold of distant objects. A rotating mass changes the geometry that defines the straightest possible paths through space and time. Matter follows those paths as matter always does, naturally and effortlessly, feeling no force at all. And from the outside, watching from beside the distant stars, we see the entire local frame appear to be carried partly around with the rotation, the gyroscopes processing, the orbits shifting, the matter swirling. All of it swept along not by any current of substance, not by any touching hand, but by the twisted geometry of a universe in which a spinning mass does not simply move through space and time, but helps shape what space and time around it can be.